Okay, hello everyone. We're going to start right now because it's already 1 minute past. We were waiting for a few more of you who couldn't make it so they can join online. So let's start. Okay, so hopefully you all were able to make it to the lab. I think 1 or 2 of you actually couldn't, so you sent me an email. Unfortunately, there's nothing we can do to repeat that lab, but hopefully those of you, whether you're online or here, who haven't been able to attend the first one can still be part of the group in the second lab. So today we're going to talk a little bit about characterization. We're going to talk about characterization of biomedical devices from biological aspects, chemical aspects, and then mechanical aspects. Okay. So what you see in the image here, and we'll talk about this extensively, is a hydrogel, right? A hydrogel, very much like jelly, okay? If you press it, it's going to crush into pieces. It doesn't have the mechanical surfaces. But the one you see on the right-hand side is actually also a hydrogel, which has a clever trick in its chemical structure design, okay, which we'll get to. As you can see, it can withstand quite a substantial load. This is actually a 10-kilogram load without breaking, okay? So it's very important to understand our materials, and what we're going to do today is we're going to talk about various aspects of these materials. So the first one, which we're going to talk about, is biological properties, okay? So it's really important to know whether these materials that we've talked about, so far we've talked about in the context of stents and in the context of valves, but we're going to talk more about the excretory system. In the next 2 weeks, we're going to talk about skin grafts, we're going to talk about the lungs, we're going to talk about a couple of the organs involved in the system, but pretty much, as you'll see, they also have the same material candidates. Okay. In all of these, we're trying to figure out whether they're biocompatible or not, but the definition of biocompatibility is a tricky one to first deal with. We sometimes talk about the effect of the implant on the body, but it's interesting that sometimes we talk about the inverse, the effect of the body on the implant. Okay, so it goes 2 ways. And when we're trying to define biocompatibility, we look at multiple tests. Okay, we look at bioactivity, which is what happens to the material, what is the chemical response of the material when it's implanted inside the body. And then we look at cytocompatibility, which is what happens to the cells, the membrane of the cells, the nuclei, whenever you actually implant that material in their proximity. We look at hemocompatibility, which is what happens to the blood contents, including the blood cells, the red blood cell, white blood cell, platelet formation, and the thrombosis and all of that. So blood contact is studied in a separate context, and then we do in vivo tests. Okay, we're going to go over these in more detail right now. So the first one we're looking at here is in terms of the cytotoxicity and the bioactivity. And the tests have been very simple for the past 30 years of testing of biomedical devices. We've only used these multi-well plates, okay, and they're very simple. You have a bunch of wells that are stacked together, basically in an array, and then you drop the object in it, very similar to what you did in the experiment. Okay, you dropped it in IPA and it didn't do much of a corrosive damage. You dropped it in the acetone, and if you take a look at the images that you'll take in week 12, you'll see that they're completely destroyed by the acetone. So this is a similar study, but instead of putting it in a solvent like alcohol or acetone, we actually put it in a biological fluid or something that simulates a biological fluid, okay? So this could be a buffer, it could be whole blood, it could be a solution that has basically all the ions that are included in the blood, but it doesn't have the cells. But the idea is very simple. You drop the specimen in these various wells and you vary the dimensions, the size. So here you can see they 3D printed a ring a super tiny ring there, and they've basically grown cells on the surface of the well, and they're trying to see proximity to the ring, the size of the ring, okay, the radial distance between the cell and the ring. How does that influence the cell survival and the metabolic rate? Now, a little bit more complex is these transwell systems, okay? And what they've done there to test biocompatibility is you've got a membrane there that's hanging from above the well, and so you can grow the cells on that membrane so the material doesn't come in direct contact with it. They grow like an endothelial layer that you have in the blood vessel or an epithelial layer that you have in the lungs, and then you drop the object in the well, and you're looking at the secretion of stuff from the object and how that influences the membrane, okay, how that influences the layer of cells on the membrane. This is called the transwell assay, and these were around again for, the transwell has been 10, 15 years. The multi-well has been there for maybe 25, 30 years, and nothing has changed about them until this company, Nemetis, came up with a chip that's sort of inspired with what you have in the integrated circuit industry and the IC and electronics space, and it uses the same processes, and you microfabricate these tiny features, okay, very tiny 50 to 100 micron channels that you can then inject the cells and grow them inside these channels as if it was a real blood vessel. And the idea here is we're keeping the high throughput aspect there. Okay, so you can use, there's 3 channels in this chip. There's a middle channel, and then there are 2 lateral channels. You can grow endothelial cells in the middle channel, and then you can introduce a substance through one channel, and then maybe study the secretion of something from the other channel. Okay, so it gives you some freedom. Or you could grow 3 types of cells in this, in the 3 walls, basically the sides of the 2 walls in the middle. So the problem with this is it's really rigid, and it's still not a good representative of human tissue. So Emulate, which we have a big Emulate center at the school level, actually designed this chip, which is based on silicone. It's a very soft, rubbery silicone, which has been around again since we were sealing the bathroom floors. Okay, that's when silicone was invented. But basically, silicone has seen wide interest from the medical space. Why is that? It's because it's biocompatible, and the reason for that is oxygen can travel through silicone, so the cells can breathe. Okay, so it's something that the cells can, first of all, adhere to the surface, and then they can grow, they can get their oxygen supply. So inside these chips, the good thing is you've got much lower stiffness. So it's unlike the plastic chips that have mechanical properties that do not resemble the tissue. This one actually does resemble the tissue very well. The problem with their chip is that it's not high throughput format, inherently because of the manufacturing process called the silicone. So they have to do it in multiple pieces. What we were thinking of doing, and we actually launched this product, microcosm, was to actually, instead of print it out of silicone, which is still very stiff, okay, it's like rubber, it's in the order of 100 kilopascals, whereas you actually are looking at around 1 to 10 kilopascals for the majority of our tissue. So we thought, why not print a hydrogel into a chamber, very similar to the chamber that you guys printed. Why not print a hydrogel and then sort of have it covalently bonded to the bottom of the chamber that can have all the fluidic circuitry in it. Okay, so that chamber is the manifold. It has the inlet and outlet for the flow, whether it's blood, whether it's nutrients, whatever. And you can design it to be, you can design it to be high throughput, very similar to what you saw in the lab. On that printer base, you could duplicate the same design. You could make much larger assays if you needed to. So the idea here was that we have 2 types of material, the rigid polymer and the hydrogel. And the good thing about that is with 3D printing, you can print these very sophisticated intertwined channels that can now host a variety of cell types. Okay, they can host, you can have a chamber that hosts hepatocytes or smooth muscle cells. You can have the channels that have endothelial cells. You can replicate a lot of the complex, geometrically complex structures in our body using the capabilities of 3D printing, and then you can do all of that in a hydrogel. Now, as you'll see, the critical challenge with hydrogels is they're very brittle. If you take a block of jelly, right, it immediately snaps. It's a little bit of force, it's going to crack, it's going to snap, and so it doesn't have the integrity that you need. So even through the printing process, with all that layering, it gets disintegrated. Okay? So I'll talk about improving the mechanical properties, but let's not go off topic too much. The problem with these in vitro tests, what do you think the problems are with these in vitro tests? I mean, you have geometry, you have the material matches the mechanical properties, you can introduce blood or nutrients. What's really the shortcoming of these devices? Complexity. Any ideas? What are we still missing from the in vivo inside the body environment? So it has a geometry, you can go as complex as you want, assume that. It has the material properties, you can have flow and shear stress. What are we missing here? Are we at the end of the line of tissue engineering discovery? Are we there already? Do we have all the complexity of tissue engineering? What's missing here? Think about anatomy. Think about the properties that you actually have in, let's say, a blood vessel. Okay? And these are 3D printed for the process that you've already seen. Okay? What's the limitation of that 3D printing process that you use? So you have the resin there, and you design, then you can print it. Yeah. Any questions? Yeah, go ahead.
Still trigger immune response.
That's true. These materials are not optimal for if you actually have whole blood, you can have an immune response. But let's assume that we've done years of optimization on the material. What's the inherent shortcoming of this approach? The printing, then putting it there, adding the cells and then the nutrients. Let's say we've got the best material and we've got the best cell line. We've got the best nutrients, okay? What's the limitation of this idea? Well, think about the 3D printing process, okay? There was one single material in that vat, right? If you needed material properties to vary across this 3D printing structure, you only had one resin there. It's impossible to then take the part out in between of every layer, put it in a different printer that has a different material in the resin that, and do multiple materials, right? So these light-based processes, as you saw, can give us very nice resolution. The sharp corners on those cubes that you saw are a good testament to that. But the problem they have is they can only do single material. Okay? So in our body, we have multitudes of materials. Okay? Every cell type likes to have a different environment, a different stiffness, a different composition. Whereas these processes only offer one single material. Now, there are ways we can solve that problem. What did we, when I explained it, you guys didn't do it in person to basically play around with the knobs, but what was one of the important factors that determined the print time? The number, yeah, exactly. How many layers you have. And then, apart from that, the time you spend per layer. The exposure time. How long do you expose? If we trigger that, okay, if we have super long exposures, you're going to have full conversion. If we have shorter exposures, you can barely get the geometry. If you have too short, if it's undercured, it can fall apart. Okay. Now, in that regime of, let's say 50% conversion is where we have a good part with structural integrity and it can hold its shape. So we have a range from 50 to 100, okay? Now, if I stop at 50 and then put it in the solvent, the mesh density is going to be much less because I'm removing the monomers, right? If I allow it to go further, 80% through the process, and now I take it out, put it in the solvent, Now I'm going to have a much more denser mesh because it's had more time to cross-link. I can control the exposure time, look, not below a threshold because then it will just not form anything. But beyond that threshold where you have the object, you can increase the exposure time to increase the stiffness. So you can basically modulate stiffness at various layers. And moreover, you can actually change the intensity of light across that state. The screen that you saw on those printers, unfortunately, it can do various intensities, just like this screen. You can have brighter spots and darker spots, but it doesn't utilize that. If it did, then different pixels across the area would see different amounts of energy. And that way you can get different amounts of cross-linking and conversion and therefore stiffnesses. So with that printer, you can achieve various stiffnesses by controlling light intensity and exposure time, but you cannot change the material. You cannot have 3 different types of material. Okay? That's still a big limitation. So this is really, I mean, you guys should know that, you know, everything comes with its own shortcomings. Okay? Now, the other problem with these in vitro approaches inherently is that, first of all, why do we move to in vivo? Because these in vitro models can model one organ, they can model one tissue. It's really difficult to have the entire body in the loop, right? You need to have all the physiology, the heart, the lungs, you've got to have the pressure drops and falls, the flow rate variations, as it is there. And to program that, you're always going to miss something. So the best scenario is you have multiple chips connected together, where fluid from one chip goes to the other and so on and so forth. So you're making sure you're conditioning the liquid medium, or that blood equivalent, so that it actually replicates what happens physiologically in the body. But still, even if you do that, there are inherent shortcomings because inside the body you have way more complexity. The multicellularity of it is one aspect of it that you don't have here. But then the reason we still use them is in vivo, we have ethical issues. Okay, that's a big one. The species that we can use, although we can use pigs and other equivalents, but the problem that we have is that, first of all, they come at a very high cost. In the US, it costs about $100,000 for one pig, study one pig. Okay, so it's very huge cost, and then also there still are the ethical issues. The relevance of species, of course, isn't there. So they've seen completely different results. About 90% of the trials that go through the animal stage don't make it to the human stage, and that's because of the irrelevance. And then you've got animal-to-animal variation, which happens in any living creature. It's not a systematic study. It's not a accurately controlled study. Okay, there's lots of variables. And so the laws and regulations, as I mentioned. So these are the issues that still convince us to use in vitro modeling. But let's say if we do in vivo, what will we do there? So in vivo, when you put an implant in the body, these are the phases that the implant is going to experience. Okay? The first phase is, the surgeon introduces it to the body, okay? And the first thing that happens is these proteins, very tiny molecules relative to everything else, they're going to adhere to the surface and form a nice cloak around it. And those same proteins are going to initiate some other events with the cells, and the cells are going to approach these implants as external bodies, and they're going to try and interrogate the material, see if it's actually a foreign body. And then gradually, the cells are going to form these giant cells that then secrete these proteins that initiate signaling cascades to then actually bring around the fibroblasts. And then the fibroblasts come and make a collagen network, a micro environment around that is like the naked tissue. And basically they encapsulate it in collagen. Now, if this was a drug-eluting stent, this completely changes its performance because now you've coated it with something that has completely different properties. Okay? So in some cases, they even model this with the simulation to make sure that they've taken account of if that's there, can we still have this molecule diffuse through, and how fast is it going to diffuse? So So to model that in vivo, they don't first, especially when you're doing an exploratory project with a new material, this is usually what you do. You take a tubing, a shunt, out of the artery and back into the vein. Okay, so you make an incision in the leg, okay, it could be for the animal or the person, or I guess the human, and then you actually draw this tubing from the artery to the vein. Sometimes you want to match the pressure drop, so you actually have a pressure pump here that can actually help you with that. But basically, you run that through your test surface. Now, in this case, I'm showing you a shunt that we tried, which was a huge shunt there, and it's actually using the exact same artery in the leg. And what we're trying to say is PEG compatible. It's polyethylene glycol. It's an acrylic material. It's an acrylic, similar to what you use to 3D print those objects with. So it's a free radical polymerization that we've used to produce this material, this object out of the material. And then what you're doing is you're doing that process, drawing the blood through that outside of the body to see if it actually can survive an hour, can survive 5 hours. Okay, how far can we go? And then usually throughout the procedure, you're using ultrasonic images and looking at those constantly, but because it's outside the body, you can just monitor the color changes, you can monitor the plaque formation, and there are probes, also ultrasonic probes that you can use on the surface of that chip to see if you've got a stable solid object or not. And then once you take it out, this image here is to demonstrate that the one on the right-hand side had, passivation, whatnot, it actually did survive, but this one didn't. Now, the problem is, a lot of the cases, we call this a good material. So this passed the test, and that's still what FDA does, and the other bodies that also here in the UK do the same. But that's not absolutely correct. This experiment checks a lot of those boxes, but unfortunately, as you know from the cardiovascular section, we have 4 scenarios, right? The blood can go in and out without any thrombosis, but it can actually form the thrombus, which is stable, what we saw there, was terrible, but it can be causing thrombosis, but the thrombus is actually traveling through. It doesn't stay. The shear rate is just detaching it. Okay? Or it could be the scenario where you've got it, basically it's collecting, but then gradually dissolving. So it's a dynamic process. It's producing these platelet coagulation clusters that then detach and go with the flow. Now, this may not cause the pig to die in this experiment, and unfortunately, they do back-to-back experiments. So 5 hours later, that pig is going to be used for another study. And then you don't know whether this effect came from previous study or not. And that's really the common practice right now. So these 2 scenarios down here, C and D, tell you that the material is biocompatible, right? It did very well, you took it out, it's now diffusible. But no, in reality, the observation is inaccurate because that is all you need to cause failure. Okay, that is all you need to cause, embolisms and all the other diseases that you've seen. So, okay. So that just to give you an idea of where we're at. But now moving on to chemical. So this is what you guys printed, and if we just slice through it, you'll see the different layers. And down there was actually these tiny branches. A little bit of a fun story for you guys. So when I arrived in the morning at 10 o'clock, realized that we hadn't started, so the TAs, they hadn't started the print in the morning, they did it the night before. And another thing was that these branches were 4 millimeters rather than 6. So when we took them off, the first batch of the 3 to have them all ready for you guys, we realized that they're hard as, rock, they're solid. So basically, your lab was almost completely terminated because of that issue. But fortunately, we got to slice them in time, in about 5 to 10 minutes, and then generate a new design and start everything over. And then I basically reduced the size of the objects a little bit, but then I made these branches a bit longer. So the optimization here is a big deal. Okay, the amount of time you spend per layer can be the reason you have delamination, can be the reason that you have rough edges, may potentially not show up immediately after, but as you come back in week 12, you'll see that it has completely destroyed the structure, it's completely disintegrated because you didn't have proper interlayer bonding. And now, as much as the post-cure chamber you think is going to help basically reinforce those and complete the conversion, it isn't. Okay? We're giving you a hint. Do not expect a stark contrast. Although it's 5 minutes, which is 300 seconds, and you spend only how many seconds per layer? 2.2 seconds, yeah. And with a base layer, you did 40 seconds. But in the cure box, you have 300 seconds. So what the hell? Why shouldn't it actually fully cure? Well, the thing is, do you guys know how these printers basically limit the penetration of light? So they are designed so that they have an absorber in the resin, and that absorber doesn't allow the light to penetrate beyond the single layer that you're curing. If it does, then it's going to penetrate through and cure the other layers above, right? And you don't want that to happen. You don't want holes in the layers above to then be blocked and clogged because the light can penetrate all the way through, okay? So you actually design the absorber so that it only goes as far as 100 microns, which is that layer of interest, and doesn't go beyond that. It basically drops off significantly. That means that in that cure box, your light coming as a flood exposure source from everywhere is also just going to go deep in for about, oh, let's say if you give it 6 minutes, okay, even if the region is a bit more inside with lower intensity, it's still going to have more time to cure, but maximum it's going to go about, 0.5 millimeter, 1 millimeter inside. Okay, that's another inherent challenge of this process. That's why you cannot just speed it up and then post-process it. Okay. So, as I mentioned, this in 3D printing is a big issue because we actually want chemical conversion. We want the parts to be fully converted, unless if we're actually intending to make an object that's less stiff. Okay. In those cases, we actually intentionally want to dissolve the polymer with the solvent to make it less stiff, okay? Which I just explained, that's one way we can modulate the stiffness. But unless it's that case, okay, we never want to have uncured or half-cured parts. We always want to have fully cured parts. But in other realms of what we use, for instance, in biodegradable materials, we actually engineer the material to degrade gradually, okay? So that's something that's actually intentional. So as I explained, the reason that happens is when you're curing this object, you're cross-linking the majority of those chains, but then a bunch of those stay as single monomers, and so they can escape that environment as soon as the solvent hits them, okay? Now, if it's a very weak solvent like IPA, can only penetrate the surface a little bit and get the residues off. But if it's a strong solvent like the acetone, it actually goes all the way in and basically takes out everything out of it. So basically, you've got about 1 day to do that. You'll see that a lot of it has already gone. Oh, that was a weird jump. Okay, I think we were right here. Okay. So basically they can escape, and that's what makes the network extremely weak, and that's what can potentially be useful, but sometimes not that useful. So in 3D printing, what happens in practice, as I mentioned, you've got that absorber. If you look at the composition of the layers, they're going to be denser and denser towards the top of each layer, and then you're going to have a gradient of conversion, even within the single layer. Because deeper into that layer, you have lower intensity because it's dropping, because of the absorption. That's why you get those delaminations and cracks. Okay? because in these layers, even within the layers, closer to the light source is going to be much higher conversion. A bit further away, it's lower, so it's weaker. So you can have this interlayer bonding be destroyed. And then, as I mentioned, the IPA actually doesn't do that, but acetone does. Now, why do you think these two were designed for this experiment? Why did we have large objects versus small objects? Why would those two differ? Yeah.
Bigger objects would have more.
But why? So,
Just more layers.
layers, okay, but then the composition, the percentage within each layer of that certain conversion is going to be the same, right? So you're basically just scaling it up to, instead of 10 layers, you're having 100, then still the composition of each layer is the same, right? So wouldn't it just scale up? And then basically the ratio would stay the same. It has to do with the post-processing I just mentioned to you. Yes, so what is that? So why does post-processing produce a size variability of conversion?
Is it the surface area? Contact with the acetone?
Great, that's one big point, yeah. But that's why we leave it in acetone for a full day, so it completely takes everything out, even the larger object. But it is a surface mediated thing. The IPA plays a role there. The washes that you do in IPA to remove the residues, the uncured material, that helps. Because the uncured material around it is going to block light penetrating in. And apart from that, I just explained how far can the light from the yellow box penetrate the walls of the object? I said just about half to 1 millimeter. Now, if this is a 1 millimeter object, that's good enough, right? This is a 1 millimeter object and it can penetrate 1 millimeters. This is perfectly going to be cured. It's going to be fully cured. If this is a 100 millimeter object and it only cures the crust around it, when you calculate and when you measure the conversion, you'll see that all the stuff inside plays a more significant role in determining the conversion. So basically, for larger objects, you should expect to see a lower conversion because these, under the post-processing conditions, receive a better improvement, better enhancement. So, as I mentioned, some people utilize this to make porous objects, so it actually helps, and some utilize it to make degradable and bioresorbable materials for stents and stuff. Now we're going to talk a little bit about surface chemistry, and the first thing which you've already heard about is contact angle and hydrophobicity. Okay? So we actually are looking for materials that are hydrophilic or phobic. Phobic, because blood, we want them to repel the blood. Okay? So we're looking for hydrophobic materials, so that's why EPPFE is a really good candidate. As you can see, it doesn't spread on the surface, and instead stays as a sphere, as a droplet. Okay? So basically, if we have low contact angle, we're looking at hydrophilic materials. Okay? So as this angle here reduces, it means that the droplet has spread. Okay? As it increases, it means the droplet is retaining its shape, it's not getting absorbed by the surface. Okay? So this is a hydrophobic versus hydrophilic material. Now, we're actually looking for the equivalent to the EPPFE. An interesting example is the leaves of trees, they actually have a coating that makes them hydrophobic. That's why you see the droplets there on the leaves. And that's not because of the surface chemistry alone, it's because of the topography. If you put it under the microscope, you'll see that it's got these cobblestone shape to it, and the droplets, they can't wet the surface because the angle, the curvature of that surface of the droplet is actually much lower than the curvature of those tiny, simple, like, the cobblestone goldstones on the surface. So it can be the chemistry of the surface or the topography of the surface. If it's the chemistry, which happens in this case, it usually has to do with the charge distribution. Okay, water is a polar molecule, right? And depending on whether your alloy there or the polymer there has, free electrons that repel the molecule, or actually attracts it because it doesn't have those valence electrons, it can actually spread or keep its shape. But remember, we're not really looking at this in detail. Remember that the chemistry isn't the only play. As I mentioned, it could be the nanomorphology, micromorphology even, of the structure, the surface that you're looking at that defines whether it's hydrophobic or hydrophilic. There are various tests. Of course, we don't have a chance to look at each of these, but to figure out what the surface properties are as a subcategory of chemical characterization, we have various tools and systems. One of them that is pretty interesting is FTIR and Raman spectroscopy. What they do is they utilize a certain wavelength of light that hits the molecules on the surface, and these molecules, the bonds are like springs. Okay, so it flex back and forth, they have a vibration. If the light coming in resonates with that vibration, it's going to send a signal that's even stronger. If it doesn't, it basically collides with it, it deconstructs that, the incoming wave. It actually then is going to come back as a much weaker wavefront. So what happens is that based on those vibrational modes that are receiving the we call photon energy, transforming it into mechanical, or basically improving it via the resonance, you can tell what composition of material you have there. Do you have double bonds, which are much stiffer than single bonds? Or do you have triple bonds, or even stiffer? But that's usually, it's more complicated when you have 10 different types of atoms. But for our stuff, the hydrocarbons, you only have carbons and hydrogen. You're only looking at the density of double bonds and triple bonds, and it's really easy to analyze the data. So we're not going to go over all of these processes, but this one's an interesting one. This is atomic force microscopy. How many of you know what atomic force microscopy is? Atomic force microscopy. So atomic force microscopy is a process where you have a probe with a very sharp tip. And when I say sharp, if you zoom in one level, that's good. If you zoom in even further, it's 1 nanometers. This distance is 1 nanometers. Okay. And this probe can actually tether and have interactions, hydrostatic interactions with molecules on the surface at a molecular level. Right? It's that part. And it's a mechanical part that's manufactured. Okay? But what it does is, it's not that it's like sliding and then sensing the topography. It's actually the force interaction. It does a bit of that, but then the majority of what it uses to improve the signal is the force interaction between the molecules and that tiny tip. This tiny tip is super sensitive. What it does is it can actually detect, okay, this is a peak, a trough. It's amazing what you can do with this. You can look at a graphene sheet, okay? You can look at a graphene sheet, and a graphene sheet is only 0.8 nanometers thick. And you can see the individual carbon atoms in that graphene sheet based on the interaction of the force interaction between the tip and these atoms. You can see that it's stronger here, weaker here. So basically, you can make a heat map of the molecules, so the atoms that you see on that surface as you're scanning through. And you know for each atom what sort of interaction force to expect. So you can produce that map and tell exactly what the structure is. That's how they found the graphene structure, by the way. Okay? And it's amazing that you can look at thicknesses of 0.8 nanometers and detect these graphene flakes on the surface of your specimen. So you may ask, how do they manufacture the tip? Because I'm interested in manufacturing, I'm going to talk a little bit about that. But I'm going to first ask you if you can guess. I mean, how could you manufacture a needle tip that's 1 nanometer? It's not 1 micron. Okay, just to put it in perspective. It's not 100 microns, which is a hair thickness. It's not 1 micron, which is 100 hair thickness and about the size of the cell, okay, even smaller. It's 1,000 times more than the cell size, than the size of the cell. How do you manufacture? And it's, you know, it looks like this. Very high aspect ratio. So it can easily be broken. Okay? It's the amazing bit of it is it's got a super high aspect ratio because you don't want forces from the surrounding. If it's a cone like that, there's lots of, you know, interaction with the surface of the cone. You want it to be a needle that tips down and goes and touches the atoms, basically. How do we manufacture something that fine? Any ideas? It's fine, take a guess. I mean, anything that you can guess is probably not going to be the answer. But, I mean, it's very clever the way these guys first did it. It's super clever. Ready to give it away? No one? Machining, lathe, milling, 3D printing, done a lot of that. So, it's interesting, they can actually make the tip in these certain geometries as well. That's 1 nanometer. Okay. Doesn't that sort of give it away what it is? The shape of that, that's not super intentional. Like, they may like to have that, but they can't, you know, they can't just design it like that. It happens naturally. Can you think of something that's happened there that caused that geometry? Yep. Stretching. Well, that's actually a very good point. If you stretch a rubbery elastic material very far, that middle section of it, that's actually the way they make these thin pipettes, the glass pipettes that have a very thin tip, and also how they make glass needles. Very good approach, actually. To be honest, these usually utilize these random observations, just like the one you mentioned, that just is a clever idea out there, you can make it this way and it works. But this one actually follows the processes that you use to make semiconductor wafers for IC chips. And does anyone know what the size of a, are you familiar with MOSFETs, metal oxide semiconductors? So basically, those are the tiniest units of an IC chip. Okay, it's a gate. It's a gate that allows the current to pass or blocks it using the secondary current. It's a basically transistor. Okay, it's one type of a transistor, but we've shrunk it down to the size where you have millions of it on your phone to make a full chip. But you know how tiny of a feature, how tiny of a wire or electrode we can manufacture that's currently used in your phone? What's the feature size that we can manufacture in Intel's latest generation IC chips? What's the size of those gates of these? Any feature, basically. So it used to be a micron, 1 micron. That's about 15 years ago. And then Intel's Andy Grove, who was a university graduate, and he actually, his thesis was studying oxygen fusion in growing silicon oxide layers. And he studied that process very well. He could precisely control the layer of semiconductor that you could, the layer of insulator that you could produce on a semiconductor. And that was really the main recipe. That they kept it secret for 10 years in Intel. Didn't tell anyone. There were 3 people who went in the room, synthesized the wafers, and came out. And that was what gave them the head start between all the other companies. And what they did was they basically invented the epitaxial growth mechanism for silicon oxide, which was then the process that revolutionized everything. And that brought it down from 1 micron to what we had 2 years ago, 14 nanometers, and this year it's 7 nanometers. Okay, so 7 nanometers is the smallest feature size. These are still smaller than that. Okay, it's interesting. The way they do it is actually pretty simple. You lay down that layer of silicon SiO2, okay, silicon oxide, and then what happens is that can protect the substrate from etching. You can then pattern that with another layer, and that layer that you, so we don't have that step here, but you put another layer on top of it, which is light curable. And with light, as you saw in the printers, you can actually narrow it down to a very small fraction of the wavelength of light. Now, the wavelength of light that we use here is 400 nanometers. So we can't go to this resolution, but they use X-ray and deep UV to reach 1 and 2 nanometer resolution pixels. So they put a layer of resin on top of that, they patterned that and removed the uncured material, and then they attacked the silicon oxide with the first etching material. So now they've patterned it there, okay? Then that silicon oxide is going to protect the substrate from the secondary etchant, which is going to now attack the substrate. And the etchant, what it does is it undercuts that layer. So if you give it too much time, it's going to try and go under. Okay? So although this is maybe 10 nanometers, 20 nanometers, but because the etchant is a diffusion process, and if you give it enough time, it digs under, it actually eats into it further and further. And at the end, if you remove that, if you use the etchant that's suitable for SiO2, the first etchant that we used, remove that covering layer, you're going to be left with this tiny protrusion with a very thin neck. It's basically utilizing some level of technology, which is in patterning, but then also some level of innovation in this clever idea of using the etching, which you can perfectly time it so that whenever it reaches here, you stop it, because it's not so fast that it's in the order of milliseconds. It takes days to do this. You can stop it. It's not days actually. It depends on what material it could be, a couple of minutes or an hour. But you can actually, it's not that fast. You can control exactly when to stop it to get that perfect shape over there. So this is how they make it. And this is also how they make a lot of the gates in the IC chips that you have in your phone. So surface texture isn't just important because of the hydrophobicity. It's also important because of the interaction with the cells. If you have a rough surface, it means you have more surface area, okay? And that means you have a greater contact with the blood. And so blood clotting is now more probable. Platelets also adhere to surfaces that are more rough, okay? Those coagulation factors have a larger area to be secreted on and then to adhere to. So all of that can influence it. This was a random, interesting observation. They still don't know why, but they did this roughening on stainless steel and realized that they could make it antibacterial. For some reason, antibacterial meaning that it doesn't just slow the growth of bacteria, but it also kills them. So topography has a significant influence, and as you can see, there are ways that we could incorporate that. Okay, we could use slippery coatings, we could use polymeric layers that are smoother on top of our backbone. We can charge the surface to actually produce an electrostatic blanket that acts as a smooth, there are lots of innovative ways we can work with topography, but I just wanted to bring it up that it's beyond just the, the appearance or the, it also surface roughness influences the flow. So you can turn it from laminar to turbulent, and that could be a big problem in terms of blood clotting. So all of these have to be characterized, and AFM is just one of these processes. There's SEM, scanning electron microscopy, which we won't go over. We have transmission electron microscopy, TEM, So there's a variety of processes that. Why do we say electron microscopy? Because that's the shortest wavelength we can get. Superfine resolution is if you use an electron. Electron is actually also a wave, right? It's also a type of wave, but it's super down there. It's a very high energy waves, even further from X-ray and stuff. So if you go to UV, deep UV, ultra deep UV, X-ray, electron beam is all the way there. So if you need very high resolution, that's why we call it electron microscopy. If you want to learn more about it, you can watch videos on YouTube about it. We're not going to cover the details here, hopefully in another course. Surface coating, the various surface coating, I'm also going to skip this one for now, but we'll talk about this maybe in the lectures. So this is your second experiment. So in these two experiments, it basically tackled two of the most important things in terms of materials and 3D printing and manufacturing. One is conversion, okay, and you always have that with polymers. Now, metals and ceramics are big, but polymers are also very big in biomedical devices, and conversion is part of all the polymers. So the process is either thermal, is using light or other means of transferring energy, but it always includes a polymerization phase, which has conversion in it. So conversion is a big factor in determining biocompatibility. The second one is diffusion. And diffusion is governed by the porosity of the material that you build. And you're going to experiment with these gels that you're going to inject in the channel between the two chambers. And you're going to look at dye diffusion to figure out what the diffusivity is. So that's what's remaining for next session. But I just wanted to conclude with this image that I started with in terms of mechanical properties. So hydrogels are now, they started off as a very, unattended material in the physics world and also in chemistry because they were super random. The chains that they had, just like polymers, could be very random. There's no uniformity. There's no coherent behavioral trend, just like metals and ceramics have. The polymers, the hydrogels don't. So that's why we were really, they're unfavorable in terms of their use in biomedical. But then we learned more and more about their physics. We got tools like rheology to study their viscoelastic properties. And that's when we started to make hydrogels that can now tackle applications that we couldn't even think of. To give you an idea, steel has a tensile strength of about 400 megapascals. Okay, so it breaks at 400 megapascals of stress. Fiberglass, which is pretty good, has 1500 megapascals of tensile strength. Carbon fiber has a little bit higher than that, well, twice that, but it's pretty much the strongest material we know of right now that's used in terms of both its strength and the strength to weight ratio. It's very lightweight. But actually, this team led by Professor Gong's lab, I think he's now in a Korean university, different institution before, they've invented this hydrogel that has 37,000 megapascals in terms of its ultimate strength. Now, it's also similar to carbon fiber and glass fiber. It's using fibers of glass, but the hydrogel is this intertwined coating that goes around it, similar to when you have carbon fiber, you actually have a secondary composite layer. And that changes the strength factor of about 25x, okay? That's amazing. Now, how does it do that? How can a jelly do that, right? Well, the idea was, they thought, what if we actually, when something breaks, what happens? When something breaks, you're exerting a lot of force. So you can look at it from a force perspective, but also from an energy perspective. You're actually putting a lot of energy on it, and you're increasing the energy, until the structure cannot take that much energy, cannot absorb it, and fracture causes, and it causes fracture, and that fracture energy it's the dissipation of that in terms of heat and other stuff. They thought, what if we have a double network, one that breaks quick and consumes all that energy on its fracture, and then the secondary one could go on for a longer period. And that's exactly what they did. So they have two networks, and the good thing is this one that breaks actually can then heal whenever it goes back. So one that breaks really fast and is brittle absorbs all the energy, and the other one produces the stretch. So we'll conclude it there. The next 2 weeks of the exclusory system, please look at the videos under this week, which are asynchronous for next week, and then we'll have one section at the end which I'll talk about. Okay, thanks a lot.